Hello, everyone. I hope everyone is safe in this big space. So, my name is Amel Sellami, and I'm a GDE in machine learning. I'm a research engineer at NSTD, and you can find me via the Twitter handler DeepLearnusa. So, one of the things that I wanted to talk about before diving into our presentation entitled "An General Introduction into Gentle Introduction into the NLP World" is that uh, let's talk about the initiative that Google is hosting. As you can see, we have 16 weeks of pure online community with various topics ranging from machine learning, Flutter, Firebase, design thinking, Kotlin, and Android. And the best part is that it's hosted by different kind of people and across the MENA region, from Morocco, Qatar, Lebanon, Algeria, Jordan, Bahrain, Tunisia, and so on and so forth. And in three kind of languages: English, Arabic, and French. So if you're more interested to know about us, please follow us in the MENA digital stream or the MENA digital website and the MENA digital feedback. So you get two more things before we dive. And if you want to have an attendance certificate, well, you can just have it with pt.le/MENA digital feedback. If you want to join the MENA digital based challenge, you can join via the MENA digital channels. And all winners who solve 5 quests between March and June wins gift box. So the plan of today is like, I'm going to try to talk about NLP, the NLP history, then the toolbox. And the toolbox meaning that all the things that we can use with Google Cloud, because obviously this week is the Google Cloud week. And what I wanted to talk about the NLP history because so that you can get like a full view of the NLP from like 2013 till nowadays. And we'll go to dive into something called transformers. And transformers are one of the most famous things in NLP nowadays. But before all of this, I wanted to share with you some of why I have chosen NLP. And you might want to ask, which is a very legitimate question, actually, by the way, but because I think literally to rise as an Arab nation, we need more translation, because translation will help us have the information more easily and democratize the information. It will be probably a lot more easier to communicate and learn if we translate more. We can have an information, the access to it actually faster in a shorter period of time. And I think AI is helpful and a predictive tool for this kind of tasks to happen, like translation. And NLP is natural language processing is very popular nowadays. And one of the tasks that were very hard to tackle is the translation part of it. So what is NLP? Well, NLP is natural language processing, usually shortened as NLP, is a branch of artificial intelligence that deals with the interaction between computers and humans using the natural language. Well, probably today we'll talk more about the deep learning frameworks or models and algorithms that exist in the NLP kind of area. So the ultimate objective of NLP is to read, decipher, understand, and make sense of the human language in a manner that is valuable. Most NLP techniques allow ML to derive meaning from human language. So what is it used for? NLP is the deriving phase behind the following common applications, which are, as you can see, Group 1, Group 2, and Group 3. We'll be more talking about the Group 3, which is machine translation, natural language generation, question answering systems. But to know more, there are other groups like lemmatization or parsing or stemming, cleanup, and tokenization. And these are things for pre-processing the data for NLP tasks. There is also the Group 2, which is which includes named entity recognitions as near, information retrieval and extractions, and so on and so forth. And the driving common applications that most of us know is, for example, for language translation, we use Google Translate. And for personal assistants such as also OK Google or Siri or Cortana or Alexa. Word processor such it could be also a word processor such as Microsoft Word or Grammarly that employs NLP to check grammatical accuracy of the text. And all of these are like NLP kind of tasks. And you might see that NLP is not just about text, it also can be about speech. But for the sake of this presentation, we're only going to tackle the text part of it. And there are other like algorithms that can be used for speech. And another question that is perhaps very, very common is that why is it difficult? Why NLP is difficult? Well, NLP is considered difficult problem in computer science because of the nature of the human language. Actually, the rules that dictate the passing of information using NLP are not easy for computers to understand. So we might understand things, but not computers. Computers does not understand us like we do humans. And to understand what rules can be difficult, some rules are not just difficult, but they are, let's say, abstract. In a way that, for example, if someone is giving a sarcastic remark to pass the information, machine does not usually understand that. Using, for example, the S character, which is like to say, for example, plural, it's not very something very intuitive for machines, but it's very common for us, right? Okay, cool. So now let's dive into the algorithms that have changed, or let's say advanced the state of the art of the algorithms. Of a long time, for the long time, the majority of methods used to study NLP problems employed shallow ML models and time-consuming handcrafted features. This led to problems like the curve of dimensionality. Well, this is a linguistic information was represented with sparse representation, high dimensional features. But with the success of word embeddings, which we'll talk about later, which is basically low dimension and distributed representation neural-based models, achieved superior results on various languages related tasks as like compared to the traditional machine learning, like SVM, logistic regression, or anything like that. So if we see, for example, the neural history of natural language processing, we see it like from 2001 until 2018. I'm not going to talk about like 2001, year 2008, but it's probably good to know them or to read about them if you're interested in the research papers, like neural language models, multitask learnings. But the things that happened that sparkled the NLP kind of state of the art nowadays is something called word embeddings. And then there are also neural networks for NLP, sequence to sequence models, attention models, memory-based networks, and pre-trained language models like for BERT, for example. So the goal today is to understand one of the best, or let's say the architecture that I think revolutionized the NLP world. And we'll probably talking about something called transformers. And for that, we need first to understand the history behind word embeddings, attention, sequence to sequence, and neural networks for NLP to be able to understand the intuition into a sense and how transformers came into a place. Okay, let's start. We'll start with word embeddings. Which are distributed vectors based on the distribution hypothesis, which is basically words appearing within similar contexts poses similar meanings. Word embeddings are pre-trained on a task where the objective is to predict a word based on its context. typically using a shallow neural network. And by shallow neural network, again, it could be 2 or 3 layers. This novel model was proposed by Benjo and colleagues on 2013. So if we see it like here in the word embeddings, we have, for example, in the first example, we have male, female. And the male, female is like we have the man into correspondence to woman and king to its correspondence the queen. Or we can see it also as like, for example, man and king lies in the same line and queen and women lies on the same line again. So these lines represent the representation in the space of a word, and this is very common techniques. So for example, each word is represented in a place in this graphic. For example, also for verb tense, we have like walking, swimming, which are in the same line if we see them because they are in the ing form, and walked and swam, they are in the same line because they are in the past form. So, and they also could be in the same line because walking and walked are in the same are derived from the same verb, which is walking, walk. So basically, this is word embeddings, and the word vector and the word vector, the vector word, and to embed syntactical and semantic information and responsible and is responsible for the wide state-of-the-art algorithms. This kind of representation, the distributed one, as we can see here in word embeddings, only gained popularity when continuous bag of words and skipgrams models were introduced to the world. You probably will be because they could okay because they could be efficiently constructing high quality word embeddings. Well, you have noticed that I've started with the year of the word embeddings, and I didn't started by the year of 2008, 2001. And the reason why is because I believe that this is the one that like fueled the NLP world. So another question that you might want to ask is that what are bug of words and skipgrams? You can probably Google them and try to find more information. But for the sake of this presentation, I'm not going to dive into them because this will be a lot more technical details into them. Okay, cool. Now we'll be talking about something called deep learning. Well, not deep learning, but everyone knows that the deep learning algorithms deep neural networks, convolutional neural networks, we have recurrent neural networks. And the ones that are usually used to deep neural network. So first, the normal one is the feed forward neural network, or DNN, or feed. We in the AI in the machine learning where we generally use feed forward neural network. We use the convolutional neural networks, and these are most likely to be used for images, but we can also use them in NLP. And there is also the recurrent neural networks, and the recurrent neural networks the sequential networks. So I wanted that one thing that I wanted to really emphasize is that usually are used convolutional neural networks are usually used for images because images are represented in sparse like kind of application in kind of images. Images are sparse like they can be in the space. For recurrent neural networks, we usually use them for NLP because they represent the order or the sequence. You'll hear me talk about the order and the sequence lots very much. That's why we usually use recurrent neural networks in natural language processing. But I'll also talk about how we use convolutional neural networks for NLP. So CNN is applied to create words or engrams that I have talked about before. I mean, high-level features. The abstract features have been used for sentiment analysis, machine translation, so on and so forth. If you're interested, Colbert and Weston were among the first researchers to apply CNN on NLP tasks. And the goal of the method was to transform words into a vector representation via a table, which resulted in a primitive word with using word embeddings approach that learn weights during the training of the network. So what is all a sentence or CNN with CNN? We first tokenize the sentence, and tokenize meaning we're going just to split the sentence in a way into words, then transform them into a word embeddings. Word embeddings I have shown you before. Word embeddings in a matrix, input embedding layer of, for example, a D dimension or I don't know, N dimension. Then a convolution filter applied on the input, again, the embeddings that we have, the word embeddings, consistently applying a filter of all possible window size. So we have a window size. This window is going to, we're going to apply it on using a filter on every possible window size that we can produce. What we produce is something called feature map, followed by a max pooling operation to reduce the size of the dimensionality. This is a very typical CNN architecture, but just to get the inside of it, reduce the size, we do max pooling to reduce the size of the dimensionality of each filter to give a fixed length output, giving the final sentence representation. So basically, all of this is that with the CNN, we convert a sentence to a sentence representation. And this is something very useful. You'll see that we'll couple CNN and RNN lately for state-of-the-art algorithms. Okay. One thing before going to the RNN is that when we increase the complexity of the basic CNN mentioned that I have mentioned, we can adapt it to perform word-based predictions. And to do so, we need a window, like a window, where for each word a fixed size window of the neighboring. So we have the word and the neighbors of that window. That word exists in a window, and that is called subsentence, is considered then a CNN, and then the CNN is applied, let's say a standalone one, and this CNN is applied to the sub-sentence, and the object is the word in the center of the window. This is called low-level classification. I'm not sure if you somehow understand me, but this is just a basic example on how to use CNN. We can say that CNNs are effective as they can mine semantic clause in contextual windows. So what we get is the representation again. Unfortunately, these CNNs, they struggle with something called, to preserve something called the sequential order, because in a sentence there is meaning is divided, is included in the sequential order of the sentence, for example. So that's why we use RNNs, or recurrent neural networks. And like their names suggest, they are recursive. They apply computation to each instance of the input. And by instance, I mean word. And conditioned on the previous computed results. And by conditioned, I mean determined. Okay, so sequences in RNN of tokens fed to a recurrent unit one by one. Okay, this is an example of an RNN. So basically, you're saying that here we have an RNN, and as you can see, this is a very basic simplification of the RNN. But just to keep in mind, we have like the input, and we have the input that has previous, what we are going to compute is using the input that we have now and the previous output of the previous layers. So are each layer uses the one that is using now and the one before. Okay, what does that mean? Well, I'll try to explain it later better, but just like just wanted to let you know that the main strength of an RNN is the capacity to memorize the results of previous computations and use it for the sake of this one. An advantage of RNN is no need for fixed length sentence. You don't have to give the same number of a sentence. So RNN used for different tasks of NLP, such as language modeling and all. What is expected as an input is a typically one-hot embeddings. If you have asked yourself, wait, what? If all units take information from the previous one, what happened to the first string, right? Well, the first string it will only take the one-hot encoding and the word embedding that I talked about. In some cases, we use the abstract representation built from a CNN model, like the one that we have talked about earlier. Simple RNNs suffer from vanishing gradients problems. That's why other variants of RNN were introduced, like LSTM, GRU, and LSTM stands for memory, long short-term memory, and GRU for gated recurrent networks. You can learn more about them if you want from their research papers. But just a quick recap. So RNNs use units. They have units, different units, and each unit uses the previous unit that was computed beforehand. And if you want to know the first unit, what it takes the word embedding or the one-hot encoding of the sentence. Okay. Okay. So we said that LSTM and GRU, and LSTM consists of three gates: input, forget, and uh, output gates, and calculate the hidden state throughout a combination of the three. Whereas GRU are similar, but they're less complex, using only two gates. That's why they are more efficient in a way. So various LSTM models have been proposed for a sequence-to-sequence mapping. Okay, so now we've talked about convolution and we've talked about LSTM, RNNs, and all these kind of things. One popular thing that I've talked about is that we generally use to combine convolution and RNN to get results. Another thing that I wanted to introduce is called sequence-to-sequence mapping or modeling. And sequence to sequence, we're going to get us to something called transformers, attention, and all of that. So the goal of today is to understand basically what is a transformer. Okay. But before that, I wanted to talk about something called attention. But please bear in mind that there are different mechanisms that you can use, like recursive neural network, reinforcement learning, and even GAN models for various NLP tasks. So it does not stop just for like RNN, LSTM, CNN. There's also GAN, RL, and all these kind of things for NLP tasks. And we'll talk about the attention mechanism. So we talked about sequence to sequence. I'll explain them later. We talked about attention and we talked about transformers. You get the full picture later. But let's just try to understand the attention mechanism, which is inspired from the need to let the decoder part of the RNN-based frameworks. Okay. Okay, so the decoder part framework, we're going to talk about the encoder and the decoder before diving into a little bit of the attention mechanisms. So when we talk about encoder and decoder, we say you have the you have the encoder and you have your decoders. So you have your input text, you encode it in a way, you get a result, and from that result, the decoders get that result and try to translate it that text, for example, or give another output. Okay, and this is a very basic kind of encoder decoder kind of architecture, and they're very famous in deep learning. So if you're interested to know more about autoencoders, encoder decoder, and all these kind of things, please try to reach to their research papers. So as I've said before, the attention mechanism is like somehow inspired from the decoder part, that the decoder part of the RNN based framework, like that I've talked about, the sequence to sequence one that I have mentioned, to use the last hidden state along with the information calculated based on the input hidden state sequence. Okay, this might be a little bit very complex in a way. So let's try understand what is sequence to sequence, what is a attention mechanism in a better way. Okay, so the transformer, one effective algorithm is called transformer for most NLP tasks. This is another reasons why again I want to talk about the transformers. Okay, so one of the things to learn is that attention describes transformers and sequence to sequence architectures. Okay, we have talked about the LSTM platforms before. So what is a sequence to sequence? And which is basically a neural network that transforms a given sequence of elements, like a sequence of words in a sentence, into another sentence. As simple as that. So basically, let's try to recap. We have the LSTM, the RNN, we have the CNN. These are architectures. We have also the encoder decoder. And basically, encoder decoder sequence to sequence architectures. This is something else. Okay. Another thing that is really interesting to know is that the sequence to sequence are like you give them a sequence of elements, they give you another sequence of elements. These models are rather good for machine translation. Why not be surprising is that a popular choice of the LSTM model. So basically, we have the sequence to sequence model, which is an encoder decoder, and with the encoder and decoder, because they are in themselves deep learning frameworks, we use the LSTM or the RNN or the GRU models in them. Okay, so meaning that the sequence, while remembering or forgetting the parts it finds important, LSTMs are good for the order part. This is why LSTMs are generally coupled with the sequence to sequence models. Okay, so we have talked about the sequence to sequence model. Now we're going to talk about, finally get to something called the transformers. Okay, the encoder takes the input sequence and maps into a higher dimension space and dimension that abstract vector is fed into the decoder, turning into an output sequence. The output that result could be in another language, symbol, copy of the input, etc. For example, we said that these type of models are rather good for the translation process. This is why one of the reasons that I wanted to talk about. Okay, let's just give an example. Let's say I want to translate from Arabic to English, as a matter of fact, or our model only understands these two languages, right? Okay, so to convert from Arabic to English, the model is going to convert the Arabic into somehow an intermediate language or an intermediate one that only the encoder and the decoder part understand and convert back that language to English. Okay, but because the decoder understands that intermediate language, so you might want to ask, what is that intermediate language, right? I mean, how can the encoder decoder? Okay, let's start. Neither the decoder nor the encoder are good at that intermediate language. Let's assume that. Okay, well, they need to train on different examples using the model, and a basic choice is given, for example, giving an LSTM on them. So basically, to learn this intermediate language is you need to give them different kind of examples so for them to be able to understand. Now, where is the transformer again? Well, I mean, to be able to understand the transformer, we need to understand again that looks at the input sequence and decides at each step which other parts of the sequence are important. Let me give you something like a metaphor or something. When reading a text, our mind tries to focus on the word we're reading, but at the same time keeps the important keywords of the text sequences into the memory to be able to provide like a context. So basically, when you're trying to when we're trying to understand the sequence, when we're trying to understand a sentence, we're not only focusing on one word in just one word, but we're trying to understand the whole context, and we're trying to extract the key words. So for the attention mechanism, the encoder does not only takes down the translation of the sentence into the intermediate language, but also units down the keywords that are important to the semantic of the sentence. I hope that somehow it was clear, because like I said, we don't only have the order, we only we we only focus about on the on the the context. Okay, give them like after that they give them to a decoder in addition to the regular translation. The new keywords make on an easier place to live for the decoder, because then our guy knows what parts of the sentence are important and which key terms give the sentence context. To get the long story short, for each input, for example, the encoder using the LSTM reads, the attention mechanism takes into account several other inputs at the same time. Okay? Plus, not only that, it decides which one are really important by attributing different weights to the face to the input. So the decoder has or receives as an input, which is encoded, the encoded sentence and the weights provided by the attention mechanism. So the decoder gets the sentence, what the encoder has encoded using the LSTM, and the weights, kind of weights provided by the attention mechanism. And one thing that really rose from that is something called attention is all you need, meaning you don't need the sequence to sequence or the LSTM. Not just you need the sequence to sequence, but the LSTM part you don't need it. Attention is all you need. All you need to do is to try to focus on the keywords. Okay? And this is historically speaking, attention was applied on LSTM models, but then came a novel research. And this novel research is what we call transformers. So transformers are simply for to say attention is all you need. Okay? So what is do a recap or something before diving into the transformers? As you can say, they're really amazing kind of they have really amazing kind of architecture. Is we have LSTMs, we have CNNs, we have sequence to sequence models, we have attention mechanisms, we have all these kind of things, and all of this, all the intuition that before they started with CNNs and LSTMs coupled. And then they decided that the sequence to sequence models are really good. So they coupled CNN, LSTMs, sorry, with the sequence to sequence models. After the sequence to sequence model, tried another. They added something called attention, and attention used basically before with LSTMs. So you have a sequence model, and these encoder decoder models are used to the these models are used to create to be coupled with the LSTMs. From the LSTMs, we can add them attentions, and these attentions are based for the keywords that they want to use or they want to focus on. Okay, all this they saw that within research that the important thing is not the LSTM. The important thing is the attention, and that's why this is where transformers came from. This is where this is where transformers are amazingly good at, and this is called attention. So what they use and what they do is only attention. So I'm not going to dive in the architecture of the transformers. As you can see, it's pretty complex one. As you can see, we have like the input on the left and the decoder is on the right, right? But both are composed of models that can be stacked on top of each other, let's say NX time. So you have the NX, and each NX has a multi-head attention, adds and norms, a feed forward, and adds and norms again in the same decoder or encoder. So basically, you might want to say, if you're going to say normally before, what they would have said, instead of the feed forward, they use the LSTM. Now for the transformers, they only use the feed forward, and the feed forward is a very basic, simple deep learner architecture. So just a piece of information: the input-output sentence of the first embedded into are first embedded into an n-dimensional space. Obviously, we cannot use strings directly. Another important question that you might want to ask: you you told us about how recurrent networks that are in member sequence, but how are we going to do that with the recurrent neural networks, but simply feed forward networks? Well, to answer that is we need to every word or part in our sequence a relative position. Since the position depends on the order of its elements, these positions are added to the representation of each word. So basically, we don't use LSTMs, but what we use now is called is use the position, the relative position of the RNNs of the feed of the word. Sorry. And one of the things that you're going to ask me, how are we going to train this one? So to train this or to do the inference testing on the sequence to sequence models is very different, because what we need, for example, when we are going to do a translation, that, for example, for two sentences that are different in different language, say for example from French to Arabic, we have an encoder. For example, it's going to be French, and a decoder in Arabic, with the decoder shifted by one position to the right, so that the model understands and not just copy paste the whole sentence. This is, for example, for training, and for inference for is another is another story. Sorry. So inference is different from the training. So we have the goal. We translate the French sentence without giving the full sentence. What we do is we refeed our model from each position of the output sequence until we came across an end of sentence token. And then meaning we're going to have like multiple runs through our model to translate the sentence. So the sentence, to be able to get it, we have to output at each time a word. Okay? Now we're going to go to the toolbox that we're going to use, and there are actually different one of them, like papers with code, Colab, TensorFlow Hub, Jupyter Hub, or Google Cloud. And I'm just going to dive a little bit so that we can have like time for the for a small kind of application. And Jupyter Lab is the best way to serve Jupyter notebooks for multiple users. It can be used in classes of students, a corporate data science group, or scientific research group. It's a multi-user hub that spawns, manage, and proxies multiple instances of the single-user Jupyter Notebook server. And one of the things that machine learning users use is Jupyters. And Jupyters are very important so that you can get a sense of what you're doing with your data and with your model, and to get like the results. Okay. Another thing that I wanted to share with you today is Papers with Goat. And Papers with Goat, it is very popular website because you can browse the state-of-the-art algorithms for specific tasks. And by specific tasks, it can be like, for example, object detection, translation, question answering, anything. And you can find the best papers and their implementation, for example, in PyTorch and or TensorFlow. And this is very interesting website. So you can also try to see and to learn from the state of the art research papers or algorithms that have been used. Another thing is Google Cloud, obviously, because we are in the cloud week, and Google Cloud offers like an AI hub, hosted repositories of plug and play AI components. Like, this provides enterprise-grade sharing capabilities, including end-to-end pipelines and out-of-the-box algorithms that let you organizing privately host AI contents to foster use and collaboration among internal developers and users. And enterprise users can find AI companies built by other teams within an organization and access AI content published by Google. So these technologies are easily deployed using Google Cloud AI and AI technologies for experimentation and production on Google Cloud and hybrid infrastructures. And the best part is that, for example, if you have your data and you give it to Google Cloud, it can easily give you a result without even having to think about the algorithm that is you want to use, because Google Cloud will try to find the best model for you to fit your data. Another thing that is really popular and really interesting is TensorFlow Hub. So TensorFlow Hub is a library for the publication, discovery, and consumption of reusable part of machine learning models. A model is a self-contained piece of TensorFlow graph, along with its weights and assets. Everyone probably heard about the TensorFlow graph and how it works, and that can be reused across different tasks in process known as transfer learning. So transfer learning is that you have, like, for example, your weights and your model, you trained it on something, you want to take that model trained into another thing and try to test it and on other, like, data or other kind of subjects on all these kind of things. So what we do is, like, we train a model with a smaller data set to improve and generalize and speed up the training. This is all that you need. And there's something also really interesting, which is Google Colab. So Google Colab, or the Collaboratory, is a cloud service offered by Google, and it's free, based on Jupyter Notebooks and intended for training and research in machine learning. It allows machine learning models to do training directly in the cloud. So without having to install anything on your computer except a browser, one thing is to mention. So one thing is to mention is that we can use the TPUs provided by Google. And TPUs are like kind of hardwares, and they really faster, or they make things faster for us when doing the training for our models. And this is provided by Google for free. So you can use your TPUs in the Google Colab. And there are actually, let's say, lots of like documentation on how to use them and how to use TPUs within the Google Colab. Okay, now thank you for your attention. This is somehow the introduction for the for the NLP. I know it's somehow a lot. These are the all the other all the links that we have shared with you throughout the presentations. And I'm just going to try to get classification with Hub very briefly. And very basic NLP like classification problem. So this notebook classifies movie reviews as a positive or negative using the text of the review. This is an example of the binary or two-class classification, an important and widely applicable kind of machine learning problem. This tutorial demonstrates the basic application of transfer learning with TensorFlow Hub and Keras. So this presentation is offered by Google. It's free. You can find it on your on the internet. So just type like text classification with Hub, and you'll find it. And you can use it. As you can see, this is a website, so you can use it very easily. And we'll use the DIBM dataset that contains the text of 50,000 movie reviews from the Internet Movie Database. These are split in 20,000 reviews for training and 25,000 reviews for testing. The training and the testing are set balanced, meaning they contain an equal number of positive and negative reviews. Okay. And the notebook uses TF.Keras, which is a high-level API to build and train models in TensorFlow and TensorFlow Hub, and which is a library and a platform for transfer learning. For more advanced text classification tutorials, you can see like in the MLCC text classification guide. Okay. So one of the things that we're going to do is first we're going to install all these things. So we have the NumPy, we have the TensorFlow, we have the TensorFlow Hub, we have the TFDS. TFDS is basically TensorFlow datasets. And TensorFlow datasets are like, you have all the things that you can find, all the datasets that you might need, or you might want to look for. So it's free, and it's very common that you want to use one of the datasets that are popular, and TensorFlow is providing this for us. So after importing all this, we download the IBM dataset, basically just normally. And as you can see, we have like the train data, the validation data, and the test data. And this is split in like 60%, 40%. So 60% for training and 40% for validation data and test data. Okay. And then we're going to try to explore the data. So let's take a moment to understand it. So as you can see, we have like the train example batch, we have the train labels batch, and this is next iter train data batch. So basically, this kind of function, it's only going to iter on the batch size and try to get the train example batch. And as you can see, for example, if we print the train example batches, for example, this is a review. This was an absolutely terrible movie. I have been known to fall asleep during films. But this is usually to the combination of things, including really tired, being warm, uncomfortable. So people are tend to share their opinions about a film or a specific kind of films. And the thing is that we are going to label our data with 0 or ones. And by 0 or ones, we mean 0 if it's negative review, and ones if it's a good review. So and as you can see, this is a very basic binary classification. Okay. Another way of doing things is that, for example, you can say for your labels, I'm going to say 0 is neutral, -1 is going to be negative, and +1 is going to be positive. And this is not going to be a binary classification, but a normal classification kind of applications. Okay. And we're going to build the model next after seeing the data, and after seeing, for example, as you can see, each label corresponds to a review. So this was absolutely terrible movie. As you can see, it's 0. So the ground truth, and the ground truth is 0, which is true after all. Okay. So the neural network is created by stacking layers, and the thing is that how are we going to represent the text, how many layers to use in the model, and how many hidden units to use for each layer, you might want to ask. So, for example, the input data consists of sentence. The labels to predict are either 0 or 1. And one way to present the text is to convert sentences into embedding vectors that we have talked about earlier. We can use pre-trained text embeddings as the first layer, which will have 3 advantages. We don't have to worry about the text processing. We can benefit from transfer learning, and the embedding has a fixed size, so it's simpler to process. So the hub is going to give you a possibility to only just get the information, the embeddings, and the vocabulary that you need to be able to classify all the information that you have in the reviews. Okay, so there are different pre-trained embedding models in the TensorFlow Hub that you can find, but we're going to use this one as provided by the tutorial. So first of thing, let's first create a keras layer that uses a TensorFlow Hub model to embed the sentences, and try try out a couple of input examples. So the embedding here is this one. With the hub layer is going, we use like hub.keras layer. We're going to have the embeddings, these embeddings, and we have the input shape and the data. Of course, it's string because the reviews are text. And then we're going to see that we have a tensor of shape 3 and 20, and this is the type. This is our first layer, or our, let's say, input, because we have the hub, and this hub is going to provide us with the input layer that we have, to just try to find the good vocabulary or the good data set that's going to help us in understanding this kind of problem. So the model is simple. It's two layers. Just we feed the first layer with hub layer. It's a sequential keras layer, and we have a dance layer which with 16 units and an activation value. And then we have a dance with the output of 1, and the output of 1 means that we have a binary classification, which is 0 or 1, which is very, very consistent. If you are more interested to know about the summary of the model, you can just say type model.summary, which gives you all the things that you need to know about your model, like, for example, total parameters, the trainable parameters, and so on and so forth. Okay? And okay, so I think this I have explained it. Okay, so now we're going to compile the model. And to compile them, we use a loss function and an optimizer. And all the models, first we create the model, then we compile it, and then we fit it. And by fitting means we are going to feed the model to the data, the data to the model. Sorry. So, for example, model.compile, we're going to have an optimizer, which is an atom, basically the one popular optimizer. We're going to have a loss binary cross entropy, and this binary cross entropy is very popular one, especially for classification and binary classification kind of tasks. And the metrics we're going to use is the accuracy. Okay, so now we're going to train the model. We're going to have like we shuffle our data, and we're having a batch. We're going to use a batch of 512, and we have like 20 epochs. So it's the same for the validation data. So as you can see, as we start, the loss is very high and the accuracy is somehow low. To understand what is if the loss or the accuracy are good or bad. So the loss down to we need the loss to be down to 0, goes to 0, and we need the accuracy to go to the 1. So as you can see here, it's very normal that the loss starts big somehow, and the accuracy is not that good, because he didn't, the accuracy is not null, because even though he has like the TensorFlow hub, the hub, he used it as the first layer. Okay, and as you can see, while training, it gets like, for example, the loss gets down to 0.17, and the accuracy gets to 0.93, which is pretty good and gives better good reviews. It means that and in order to be able, this is for training, and in order to be able to say that our model is good, is this we do the evaluation of our model, and for this we're going to say, for example, results. We're going to have the model evaluate, and we get the results, which is, for example, the loss is 0.3 and the accuracy is 0.85. And as you can see, the validation of the test data, or the validation data, is less than the accuracy of the training model, which is very normal, because this is how, like, this is why this is how machine learning tends to learn, because the data, the validation data, the model didn't see it before. And you can say that, you can argue that 0.85 is very low. It's not a good result, because it means that out of, like, say, 10, 10, 10, 10 reviews, you're going to get 8.51 true, and the other 1.5 is going to get them wrong. And for that, this is a very basic model. As you can see here, we have, like, for example, the train. We have, like, the model that we have, the summary of it, and it's very. So to be able to get better results, you need to use, like, more complex models. Okay. I think for me this is all for today. I might want to go and see if there are any questions. Okay. Well, pre-trained embeddings, or it's not more of pre-trained embeddings, but like, we have pre-trained weights, and these weights can be used to identify things. And for example, if you say, how am I going, this is very popular, and this is something called transfer learning. So if you want to use, for example, you have a model, and that model, you made it learn, for example, on a task of, for example, let's say translation, and this translation is from, for example, from Arabic to English, or from English to Arabic. Okay. And if you're going to translate from English to Arabic, your model have learned somehow certain things in a way. For example, if you want to do the other way around, from Arabic to English, you can use, like, these weights, and all these weights that you have used before, that you have trained your model on before, to be able to be used for the model, for the next way, or your next task. This is very popular in deep learning. I'm not sure if you have understand me or not. I hope so. Okay. If there are no any other questions, if you have any questions, please submit them before the end of the time, so that I can answer them. Okay. Okay, I think I didn't see them. Okay. Okay. Well, can you tell us about the attention mechanism applied on sequence classification? It's clear on ML T class, but it's not obvious when it comes to sequence classification. Mm, well, generally we use, as far as I know, generally we use the attention mechanism, or the sequence classification, or generally the attention mechanism are used for example, for kind of translation on, or question answering, not just a simple basic classification. I'm not sure. I think I've never seen this before. So yeah, and okay. Those classification models don't usually contain encoder-decoder blocks. Okay. So basically, yes, a model, the sequence to sequence is like basically an encoder-decoder. I know the classification models don't use the sequence classifications, but for to get just to do a quick recap, you have the sequence to sequence, and this sequence to sequence are encoders and decoders, and these encoders and decoders are basically like you have, for example, the encoder which uses LSTM and also the attention mechanism, and we have the decoder also uses an LSTM and the attention mechanism, and this is basically not for classification models. Basically, this is for, like I said, kind of more like complex models, for example, for translation or for any kind of question answering and all these kind of things. But for example, for classifications, we generally use like normal LSTM or deep learning just to get like, or CNN, for example, CNNs and then and then LSTM. Yeah. Okay. Okay, thank you very much for your time and your and for stopping by. See you hopefully next time, and until then, stay safe and bye bye.